A rail car is set up to have a 2.5 kilogram mass suspended from a string. In both situations below, the mass is at rest relative to the car. Okay? So at rest means that it's an equilibrium. It's a steady state. Maybe not equilibrium. Maybe yes. I'm going to say equilibrium. Steady state. Basically means that if you take time frame shot at one point and look at the same point like 3 minutes later, be the same. Note the arrow in the figure illustrates a range of possible positions for the mass. Okay, so this arrow means possible position, not that the mass is swinging. Okay? So if the rail car is moving at a constant speed relative to the ground, a stationary observer on the ground will see the mass to be hanging straight down. Okay, so the key point to think of here, so I think this is true to start with. So if we look at our kinematic equations, we have A equals A, V equals AT plus V naught, X equals 1/2 AT squared plus V naught T plus X naught. And the reason I want to bring this up is because this says constant speed relative to the ground. So if we look at this one for speed, constant speed means a zero acceleration. So if this value, which is V final, equals V initial, and we assume that T can change, that would imply that acceleration here has to equal 0. So if acceleration is 0, then you're not going to have any net force on it. So think of it this way. So sum of all forces equals mass times acceleration. So if the car is moving at a constant speed, it means the car is not providing any acceleration to the mass, which means that there isn't going to be any acceleration left or right. So if we draw a free body diagram, as is often desired, draw a mass like that, we're going to have force of gravity, and then we'll have tension of the string, but the acceleration to either side will be 0 because of what we discussed right here of the rail car moving at a constant speed. Constant speed, as you can see through kinematic equations, means acceleration is 0, and therefore the acceleration to left or right, horizontal, will be 0. Another way to kind of remember that is acceleration is the derivative of velocity with respect to time. So if you have speed, I'll write s, measured in meters per second, take the derivative, that's supposed to be an s. With respect to time, you're going to acceleration, which will be meters per second squared. If you're familiar with calculus, kind of makes sense. And so since another way of phrasing the derivative is the slope of something that is constant, or the slope of a constant, will be 0. So the big thing here is derivative of a constant is 0. We have, therefore, 0 acceleration left or right, which means it's going to be hanging straight up and down, even though it's moving. Now, your thought process might be like, this doesn't make any sense. I'm pretty sure I've seen rail cars moving down the rail with something similar to this, some sort of similar setup. And one of the reasons this might intuitively not really click is because in reality it would have wind resistance. So you'd have force wind going this direction, force wind, which would cause tension to kind of be off at an angle, which would cause it not to be straight up and down. We're going to assume in this case, since wind was not mentioned, or maybe we can assume that this is blocking the wind. But even if it was, then wind would probably come back. Doesn't matter. The point is, we're assuming wind doesn't matter. So that's why in reality you probably wouldn't see this situation, but it would, in this sort of idealized scenario, it does make sense that the weight would be straight up and down. Okay. Now, if the rail car is accelerating forward with an acceleration of 4 meters per second squared, what is the tension in the string? Okay. So now we're going to look at it. So we have car moving forward. So we're going to have string going this way. We're going to have 4 meters per second going this way. And we're going to have 9.8 meters per second squared, going down. That's due to gravity. And then we're going to have some sort of tension here at some sort of angle pulling it up. So we're trying to find out what's the magnitude of the tension. We're not concerned about the direction, just the magnitude. So to find this, we're going to convert these these accelerations into forces. So force equals mass times acceleration. Since tension is a force, so we know we have 2.5 kilograms. So I'll do 4 times 2.5. I think that's 10. I wonder if I can just do this in my head. We're going to try. This 9.8, which is basically 10, times 2.5. This gives us 25. So we have 25 plus 10. So we have 35. That doesn't make any sense at all. No, because we need to square them. So we have 10 and 25. So these are our forces. These will be newtons. And so when this tension in this direction from the string, when we break it down into components, it's going to have to exactly cancel everything out. And that's because of this phrase up here, the mass is at rest relative to the car, which means there's no net acceleration at this point, or no net force as well, because the tension will be canceling out both the acceleration of the rail car and the acceleration due to gravity. So from this point then, we're going to have to do this through adding vectors. So we're going to have to move this, so messy. I'm going to pretend that adding another color helps simplify things. So the 9.8 goes over here. We want to find this net acceleration, or as we've converted it to, force. So we already found that this force, draw a triangle like this. I said this force was 10, which is 4 times 2.5. I called this one 25 because 9.8, which is almost 10, times 2.5 is 25. Square both of them. I'm going to use a calculator. Calculator, clear, 10 squared, that's 100. 25 squared, which is 625, so we should get about 725. 725, second square root, second answer, we get 26.925. 26.925, and that will be this hypotenuse right here, and that will be the force, which is about this one. I'm going to redo it real quick, just with 9.8 instead of my approximated 10. So plus quantity 9.8 times 25 times 2.5 squared. Second square root, second answer. That gives us 26.46. So 26.46 is the actual close to answer. When I estimated 9.8 is 10, then I got that. So 26.46, which is 26.5. So I know I kind of went through that in the most complicated, convoluted way possible. And for that, I apologize. But the way we found the acceleration was, we know we have a vector of 4 meters per second going to the left. We have 9.8 meters per second going down to gravity. And that's going to have to be canceled out by tension. We converted the accelerations to forces using force equals mass times acceleration. We then set them equal to each other and solved for the hypotenuse, which would be equivalent to the tension, which was 26.46, which is about 26.5. So these kind of problems can get actually fairly complicated. This one's a relatively simplified example, which is nice. Hope that helped. I will see you on the next problem.